Okay, folks, hello and welcome back. Happy Wednesday morning to you. We have been, that's just too dang loud for me to pay attention. Let's see, microphones, whoa. All right, that seems a little less in your face. All right, we have been talking about reactions of alcohols. Our theme has been turning OH into a good leaving group. We have used a strong acid to do this and then substitute the OH with a halide such as Cl or Br, but we've learned to be aware of carbocation rearrangement. And we've also learned that the mechanism is for secondary and tertiary alcohols is SN1, so you're going to lose stereochemistry. So if you want to avoid carbocation rearrangement and avoid getting both configurations at a stereocenter, if you make a stereocenter, you can use PBr3, which converts the OH to a good leaving group, and then bromide comes in from the backside and does substitution chemistry. You can do the same thing with SOCl2 and pyridine, turn the OH into a good leaving group, backside attack to give you the new chloride. I really don't care that you know the mechanisms of these reactions, though if it helps you, it's certainly not going to be harmful to know. We also talked about how you can do elimination reactions without a carbocation intermediate. POCl3 is your reagent of choice. Pyridine, in some cases you need a base to remove the proton from the alcohol once it attacks either of these reagents. That's a detail that doesn't matter as far as I'm concerned. However, it's going to be totally unclear why POCl3 does elimination, whereas SOCl2 or PBr3 do not. And I just said, at some level in synthetic organic chemistry, if it works, you can use it even if you don't understand all the details. If that makes you uncomfortable, then you should stop using any technology in your iPhone at all, or your smartphone at all, because you probably, most of us don't understand all the details of how those work either. Finally, we talked about how you can convert the OH into a good leaving group, but get a stable molecule, the tosylate, that for whatever reason doesn't have the Cl come in and attack from the backside. And this allows you, the tosylate allows you to have some more stereochemical options. For example, if I wanted, I could use this pathway or this pathway to do a series of substitution reactions, and I would have opposite stereochemical outcomes, and we talked about that last time. We may review that again. One thing I didn't tell you is that you can also do dehydration or elimination reactions with alcohols under acid catalyzed conditions, but you need to use an acid where the conjugate base is really not that great of a nucleophile. So your text uses H2SO4, that's sulfuric acid. By the way, all of these concentrated acids, HCl, HBr, H2SO4, if you go to the stockroom and buy a bottle of these, they come in water. So you can always assume that water is present when you're using those acids because you can't buy them without water. So if you use H2SO4 and water, I'm going to abbreviate the structure of H2SO4 with HA and the mechanism I'm going to show you. We protonate the OH group. Same first step as the reactions above with HBr or HCl. That turns OH into a good enough leaving group, and it leaves. And the reason it leaves and nothing else happens is the fact that the conjugate H2, no, it is that one, okay, sorry. The conjugate base of H2SO4 is not a good nucleophile. And so the OH leaves, you get a carbocationic intermediate. At that stage, you should beware the possibility of 1,2 hydride shift because you have a tertiary carbon adjacent to a secondary carbocation, and if you did the rearrangement, you could convert that secondary carbocation into a more stable tertiary carbocation. At this stage, I told you in chapter 7 and 8 that generally SN1 and E1 are competitive. Then I turned around at the beginning of this chapter and said, well, actually, we only get substitution products for HCl, and the answer for why that was I don't know. And unfortunately, there's going to be another I don't know here. With sulfuric acid, you don't get substitution products. Instead, you just get elimination products. So that may be unsatisfying. I think you're seeing there are some details if you want to be able to plan syntheses in a sensible way that you're going to have to learn how to remember. We can do elimination reactions from any beta proton that can line up with the empty p orbital on the positively charged carbon. So we can get any of the following elimination products. Both of these two are non-rearranged. You could get, let's see, that's another beta proton, isn't it? You could get that rearranged product. And then if you remove this beta proton, you'd actually get that product. So you get a mixture. Removing this beta proton would give you the same product as removing this beta proton would. Okay, so you're going to get a mixture of alkene products. If you had to choose which was the major one, you'd choose the more substituted one. But again, under acid catalyzed conditions like this, you must be aware of the looming specter of carbocation rearrangement. I will point out that as many of you, let me say this, as some of you may have learned recently, if you look at bonds broken versus bonds formed in this reaction, this is actually slightly uphill in energy. The alkene product is not as stable as the starting material. So that suggests if a reaction's uphill in energy at equilibrium, you should have more starting materials than you have products. That seems like a cruddy reaction, and it is, but there's a workaround, and that is to simply do something you learned in general chemistry. The way equilibrium works is that the forward rate and the forward rate divided by the backward rate is basically the equilibrium constant. So if you remove product, that dramatically lowers the backward rate of the reaction, because the backward rate of the reaction is K minus 1 times concentration of product or whatever. So if you continue to remove this, that backward rate never gets a chance to match the forward rate. That's called Le Chatelier's principle. And so it turns out you can distill the boiling point of an alkene should be lower than the boiling point of an alcohol, because the intermolecular forces, hydrogen bonding over here, stronger than just the van der Waals interactions that are available over here. And so you can actually, in a reaction vessel, you could actually boil off the alkene in the presence of the alcohol, and that will push this reaction to completion. I'm telling you this not because I anticipate that you'll ever do this reaction. You might in the 353 lab. Frankly, sulfuric acid is a very reactive reagent, and though we use it willy-nilly here, people have found that it's a terrible thing to use for most organic compounds if you don't want your desired product to turn into a gooey tar. But I'm telling you this because we're going to turn around in chapter 10 and start with the alkene. And under identical conditions, we're going to go back to the alcohol. And you're going to ask, why and how can we do this? And the answer is, remember, this direction forward, alcohol to alkene, was uphill in energy anyway. So we actually have to do something special to get the alkene product. That being said, I'm going to assume that you all know that. And so if you use a reaction where you're using H2SO4 to convert the alcohol into the alkene, I'm going to assume whatever practical issues are taken care of and you can do that reaction. Yeah.
Just want to make sure I'm understanding that the secondary product, I guess, over there, that the one hydrogen down on the bottom, there are two more hydrogens, but they would just be on the secondary one.
Mm-hmm.
There's two more hydrogens on the bottom, right?
Oh, sure. They're all identical because of the methyl group, so it doesn't matter which one gets removed. So a similar issue over here. You've got an identical proton on two identical protons on two identical methyl groups, so the product you get from each of those is the same. Right. Okay, others? Yeah?
Are we checking on to chapter 10 now, or?
No, we still got epoxides to do. Yeah?
I know you mentioned that sulfuric acid is one we'll never see substitution reactions for.
Yeah.
Does that include TSOH as well?
Does that include TSOH as well? This chapter is a mess. I hate when I have to tell you I don't actually hate telling you I don't know, but what I hate is the idea that you shouldn't ask questions, because you totally should. I just don't have satisfying answers to a lot of them. So you mentioned TSOH. What on earth is that? Sulfuric acid is in water, and it's a really, really strong reactive reagent. So it's not going to be suited for all situations, particularly if your starting material is not water soluble. So organic chemists have developed an alternative organic soluble equivalent of H2SO4. And that is, you're going to love this, para-toluene sulfonic acid. Okay, it's related to the tosyl chloride and the tosylate sort of reagent that you've seen before. Methyl group here, benzene ring, that's where the toluene comes from. And then this is the sulfonic acid. You may have seen something like this before because, I told you that the TS in the tosylate reagent is actually a sulfonic acid ester, basically. So the conjugate base of TSOH, that's the abbreviation we'll use for this, the conjugate base of TSOH is this group if it left. Not the same thing as TSCl, but they're related. That's not important. I'm just pausing to help you see the connections, because I know people get confused on what on earth TSOH is relative to TSCl. TSCl converts the alcohol into the tosylate, or the sulfonic acid ester, and then that can be a good leaving group. But if you use TSOH, this is a strong organic soluble acid, and so you can do elimination chemistry with TSOH, but again, the mechanism is very E1, so you must beware the evil carbocation rearrangement. Well, it's not necessarily evil, but the possibility of it. So if you wanted to eliminate this alcohol and you used para-toluene sulfonic acid, you're going to generate first a carbocationic intermediate. Then you're going to have the possibility of doing the 1,2 methyl shift to get the more stable tertiary carbocation. And then you have to consider elimination products from all of those possibilities. Oops, that's not what we wanted. Here's a beta proton. Here's another beta proton, and then in orange we'll do that one, leading to the following products. This is one you get from the non-rearranged carbocationic intermediate. If you remove the orange beta proton, you get this one. And if you remove the blue beta proton, you get a more substituted, more stable, and probably major alkene product. So essentially, TSOH and H2SO4 do exactly the same thing. You can use them interchangeably. The rhyme or reason for using one versus the other is, as I told you, TSOH is organic solvent soluble, whereas H2SO4 in water isn't. And so depending on the molecule you're using, you might want to use either choice. Having multiple choices where there's no distinction, actually I know drives you crazy. And I'm doing it because the text does it. I want you to be aware of how to use both reagents, but you may use them interchangeably. So you need to recognize them all, but you can use them interchangeably. Okay, questions? Yeah.
Are both of these specifically typically happen for an OH group? They'll lock on and that will be a leaving group, or is there other situations too?
Sorry, will both of them?
So in all the cases you've shown so far, you're using OH as the initial leaving group. Will it always be that way?
So all of these things I've shown you so far involve modification of the OH group to something else before it can leave, because OH minus is a bad leaving group. Yeah.
Okay, but like you could have this, like the TSOH or something else, or the H2SO4 lock onto something else, and that could still be leaving group, or is that not the idea?
So you're saying something about sulfuric acid locking onto something else. What is the something else?
Anything that's not OH.
Oh, so I guess maybe this is a question about selectivity. If you have an OH group in the molecule and other stuff, is there a possibility that sulfuric acid might modify some other stuff? Yes. So, I feel like that's fairly far away before we have to worry about that. But in general, yes, as an organic chemist, you have to be concerned about reaction selectivity. And sometimes two different functional groups will react with the same reagent to do, and you only want one to happen. And so there is a strategy for dealing with that, and I'm trying to remember when that comes up. Not yet, anyway. All right. Anything else? Yeah.
So if you have a primary alcohol that undergoes an E2 reaction with dehydration, is that correct?
If you have a primary alcohol, does the mechanism E2? Yes, because it has to be, because the primary carbocation is too unstable.
Okay. So that being said, why is it faster for like a tertiary alcohol to undergo E1, whereas a primary is not as fast with E1?
Yeah, your text does say that for alcohols it's faster for secondary and tertiary. I don't know. I mean, that's just an empirical observation. And I don't have a good reason for it other than to say that the thing that does the elimination is the conjugate base of a really strong acid. So it's possible that it's good enough, this conjugate base is good enough to remove the proton in the carbocationic intermediate, but perhaps not for the primary alcohol where there is no carbocation intermediate. So that's, I say hand wavy and I feel like I need to do this. I mean, that's sort of my guess. I really will not ask you a question on a test. Which alcohol reacts faster and what is the mechanism? I might want you to know the mechanism, but I don't care which alcohol reacts faster. Right? Okay. Before we can move on from chapter 9, we need to talk about the epoxide, because the epoxide is a lovely exception to everything you've learned about how a negatively charged oxygen, as in an alkoxide or an OH minus, is a terrible leaving group. So let me introduce to you the functional group epoxide. We're going to talk about what it's useful for at the end. I'm just so excited. I'll give you a preview. Look at all that stuff down there. Are you excited to memorize that and write all of that down? That's actually how epoxy resin and glue works, and it's kind of fun. But before we get there, we need to learn a little bit about the epoxide structure. So, what is an epoxide? It is a three-membered ring containing an oxygen. So it's an oxygen version of cyclopropane. And let's talk just briefly about how to draw these. I'm drawing a very simple epoxide. Each of these carbons you can think of as sp3 hybridized, though you've got the bond angle strain issue that we talked about before for cyclopropane rings. So we can call this highly strained. All right. You can draw an epoxide with the 3 atoms in the ring in the plane of the page, in which case then you would have up substituents coming towards you with wedges and then dashed substituents going back into the page. Alternatively, you could draw an epoxide like this, where one of the bonds in the epoxide ring is in the plane of the page. We'll put one of the substituents down here in the plane of the page, and then we'll have going back into the page the hydrogens. You can draw this either way. Both of those are equivalent. If you're struggling to see that, make a model. All you're really doing is you're taking the flat epoxide in the plane of the page and you're tipping it upward just a little bit so that the oxygen is angled out towards you, but those hydrogens that used to be pointing towards you get tipped down into the page. Maybe it's worth looking at an epoxide in Spartan, if we can draw one. That wasn't it. Okay, so this is the view of the epoxide that we did here. All of these atoms are in the plane of the page, and you've got a couple of hydrogens coming out at you and a couple going back into the page. And then this is the view I drew below, maybe like this, where the carbon-oxygen bonds are coming out at you. These would be wedges, these would be in the plane of the page and therefore just be lines, and then this would be a dash. Does that make sense? People struggle with spatial reasoning sometimes with epoxides, and we're going to talk about reactions they can do, and shape and stereochemistry is actually really important, so being able to understand the shape of the epoxide is really key. I wonder if this, oh, it's in the database. Do we dare? Whoa. That's the, yeah, I don't think we dare. That's the Lumo. Whoa, yeah, we really don't care. Sometimes the MO picture is not actually helpful. Okay, so the epoxide is highly strained. Because of that, we're going to be able to do SN2 chemistry, and the negatively charged oxygen is going to be a leaving group. And that's unfavorable, but we've already paid for it energetically because the ring is so highly strained. In other words, if it's for a regular alcohol, it's tough to take a nucleophile, a regular alcohol or an ether, it's tough to take a nucleophile and make the OR minus be a leaving group. If you take the starting material and make it highly strained, suddenly it becomes thermodynamically favorable. So for the epoxide, it's going to be totally fine for the negatively charged oxygen to leave. So we can take a nucleophile and do an SN2 reaction. I've deliberately chosen an epoxide where the 2 carbons are equivalent. We're not always going to be so fortunate, but at this introductory stage, I'm going to show you how to draw the mechanism for opening of an epoxide from either of these perspectives, just because it may make more sense for you one perspective versus another. So take your nucleophile, whatever it is, it's going to be sort of general. Let's suppose it's negatively charged. We're going to open up the epoxide via backside attack, as we would do for the SN2 reaction. The carbon-oxygen bond will break, and the negative charge will go on to the oxygen. You get, because it's SN2, we would see if carbon A were a stereocenter, we would see inversion of stereochemical configuration. I'm going to draw the bond with the nucleophile opposite the bond with the O- group to indicate that the nucleophile came in via backside attack. The stereocenter, or the carbon B, doesn't get inverted. The configuration of the oxygen on carbon B stays the same. Carbon A does get inverted, and the protons pop up this way. This is one view of the SN2 reaction. Alternatively, you could show the nucleophile attacking backside attack here. And from that perspective, I would draw the negatively charged oxygen on carbon B here, and I'm going to keep carbon B unchanged relative to the way it was originally drawn. Then I'm going to notice that the nucleophile came in opposite the OH group, so I'm going to draw the nucleophile here. The hydrogen that used to be going back into the page pops up because of inversion of the stereocenter, and then I will keep this one sort of in the same place. You may need to use a model set to convince yourself that those two views are indeed identical structurally. But you can draw epoxide opening either way. Same basic process is happening. I'm going to check real quickly to see whether the iROA app has any epoxide stuff in it. I'm not seeing any epoxide, so oh well. Very sad. Maybe someday. Okay. Questions so far? Yeah.
Why doesn't it just fall apart on its own?
Why doesn't it fall apart on its own? If it did, I guess the question is, why isn't the sort of SN1 reaction possible here, where the epoxide simply goes like this and leaves a positive charge on this carbon? Because if it did, that negatively charged oxygen would immediately attack the empty p orbital and close up the ring. Yeah. Okay, other questions? Yeah.
Why do you call those stereocenters if they're
You're right, they are not stereocenters, but I'm preparing you for the future examples when they will be stereocenters. Yep. Okay, others? Well, first, am I really going to show a negatively charged oxygen as being part of the product? No, because a lot of times, because in organic chemistry, when we isolate organic molecules, our techniques for doing so usually mean that those molecules are neutral. So you'll learn in the organic lab, there's this thing called aqueous workup. What that means is you take your organic product that's in an organic solvent, you expose it, you dump water on top of that and shake it up, and stuff that needs to get protonated does. Sometimes the water is acidic, sometimes it involves sodium bicarbonate. Details don't matter, but aqueous workup provides an opportunity for you to pick up a proton on a negatively charged oxygen. Presumably, whatever you're using for aqueous workup involves some kind of acidic proton that's at least acidic enough to protonate a negatively charged oxygen. So I guess we can do the same thing down here, just two different views. So the product of an epoxide opening is going to have a nucleophile on carbon A and an OH group on carbon B. This is an important structural pattern. In the future, you're going to face situations where I say, propose a synthesis for the following molecule. And you'll have to look at that and think, okay, what reactions do I know of that give that particular structural pattern as a product? The pattern to which I'm referring here is a 1-2 kind of substitution of something that was a nucleophile and then an alcohol. If you see on adjacent carbons, that's the 1-2 part, an OH group and something that could have been a nucleophile, probably you could have made that by opening up an epoxide. We'll give you some examples of that in a little bit. Let's talk about epoxide opening regioselectivity. We'll do this at the same time as we do the stereochemistry. Go ahead.
Sorry, before we move on, as far as when the epoxide opens,
Yeah.
Do the hydrogens have the same stereochemistry? Do the ones that are wedges stay wedges?
We're going to see that when the epoxide opens, we get inversion. If this were a stereocenter, we would get inversion of configuration at the carbon where the nucleophile attacks, just like in the SN2 reaction. At the other carbon, because nothing changes there, only the oxygen leaves, that one stays the same. Yeah?
And the second example that you used, it's just the same molecule twice.
Yeah, different view.
I guess on the very far right, it's not a different view. It's a different.
Oh, okay. We happy now? I'm sorry, I'm just teasing you. Yeah.
So with the wedges and dashes, it really doesn't matter which one's pointing out accordingly because it's a single carbon-carbon bond, so it can rotate.
Okay. It doesn't matter here because these aren't stereocenters. And I don't have to draw it specifically this way because you can rotate around carbon-carbon bonds.
Right,
Yeah.
like that's okay, right?
Yeah.
Okay.
So let me just maybe give you some examples in which stereocenters are involved. Why not? This is fun. Okay, so we'll do this epoxide. Is that epoxide chiral? Why is it not chiral? Plane of symmetry, right down the middle. Are A and B stereocenters? Yes, they are. Therefore, what kind of not chiral molecule is this? It is a meso compound. Good. See, you cannot jettison what you learned in chapter 5. It's going to continue to be important. All right, let's choose as a nucleophile, in this case, let's just choose OH minus. All right? So this will be stereochemical issues associated with epoxide opening. We'll do the regiochemical issues in just a little bit. Right, so because are carbons A and B equivalent to each other? By symmetry, yes, plane of symmetry. So we have to get, if they're identical to each other, we have to attack either one with equal frequency. Right now, let's just say that we're going to attack carbon A. We can come back and see what happens when we attack carbon B instead, all right? So, taking this view of the epoxide, we attack carbon A. That's really attacking the carbon-oxygen sigma star, which is presumably low enough in energy to attack because of this ring strain. In any case, as you attack, the oxygen carbon A bond breaks and electrons move on to the oxygen, and you get this intermediate. Carbon B stays exactly the same. Carbon A, we need to show inversion of configuration. And to do that, from our perspective here, what's above the page and what's below the page are going to stay above and below the page, but whereas they were oriented to the bottom of the page, now they're going to go up to the top. That's how we're going to show inversion of configuration here. All right, and if you'll allow me, I'm going to neglect the aqueous workup part of the mechanism. We'll use the double arrow there to indicate that you get a negatively charged intermediate first and then we protonate it. All right. Everybody okay with that being a product of the reaction? By the way, just structurally, it's going to be useful to look at structural trends and patterns. This is a 1,2 diol. Now, is this molecule chiral? You may want to check. I mean, it looks like we're in mesocompound territory. So one way you can check is just to rotate around the carbon-carbon bond in the middle to get the like groups, at least the OH groups, eclipsed with each other. As I do that, the methyl group should be a wedge pointing downward, and then the hydrogen should be here. Right? So no plane of symmetry, that is chiral. Right? Okay, well, am I allowed to make something that's chiral from a non-chiral starting material? Sure, as long as you got to make the other enantiomer. And we get the other enantiomer from attack of carbon B. So I'm just going to show that briefly. If the OH attacks the other carbon, B, we're going to have this as our product. Notice that those two are actually, whoa, they were, these two are actually mirror images of each other. We can rotate around the carbon-carbon bond to check for the tricky meso compound. And what we would see is this, which, we can simplify our drawing up here to get the extraneous stuff away. You can see those are enantiomers, right? So when we open up the epoxide, this is a reaction that's called stereospecific. The SN2 reaction is stereospecific, meaning the mechanism requires a stereochemical consequence. All right? Now, to illustrate this, let's choose a different epoxide diastereomer. Let's, instead of choosing the meso epoxide, let's choose one of the two enantiomers where one methyl group is up and the other methyl group is back. Now that is a chiral starting material. Or rather, that starting material is chiral. Carbons A and B are actually still identical, but this time because of an axis of symmetry. You can see that if I drew a line in the plane of the page bisecting this oxygen and this carbon-carbon bond, and I spun around 180 degrees, I'd still have the same thing. So as I consider this mechanism, I still have to worry about, because carbons A and B are still identical, just in a different way, I do have to be concerned about attack of either of them as a possibility. Let's show just attack of carbon A. Again, we will skip the aqueous workup proton transfer stage. Carbon B stays the same. Carbon A gets the OH group here. The methyl group is still coming out at us, but now oriented towards the top of the page. The proton is still going away from us, oriented towards the bottom of the page. It might be useful, again, this is a 1,2 diol, it might be useful to rotate around carbon-carbon bonds to put like groups eclipsed in this case so that we can check for planes of symmetry. Is this product chiral? No, it's a meso compound. If we were to attack carbon A, I'm sorry, forgive me, if we were to attack carbon B instead, and I'll abbreviate this, we would get this as a product. What is the relationship between those two compounds? Enantiomers, right? No. Don't let that happen to you again. Many of you got stuff like that wrong on the exam. Do not let it happen to you again. Those are both the same meso compound. So one thing I want to, this is one way to illustrate the fact that the reaction has stereochemical consequences. These two starting materials that we used in these two reactions, we'll call 1 and 2. These two starting materials are diastereomers. The products are also diastereomers. In a stereospecific reaction, if you start with one diastereomer and you carry it through, there is a consequence that you have to get. And if you start with another diastereomer, you're going to get a different consequence. And those two options, you started with diastereomers, you end with diastereomers. The mechanism controls the stereochemistry. Okay? So this is an issue of, this is a classic example of can you follow through the stereochemical consequences of this reaction, which is inversion of stereochemistry. And I tell you, I love to ask questions where I do something like this. Let's see, add page? Yes, where I add a page, that's what I like. Where I say, okay, I want you to make for me this molecule. What was the starting material? And one of the options is going to be this epoxide, and another option is going to be that epoxide. See, I'm telling you my dastardly deeds. It's going to get worse because we're going to learn how to make the epoxide, and then I'm going to tell you you have to start with either this or that. Dun, dun, dun. I feel like I need like some sound effects here. Maybe I can rig that up on the iPad. I can just push. All right. Okay, we need to deal with regioselectivity of epoxide opening, and we're going to do that, but I want to use the last couple of minutes to tell you about epoxides in glues and resins. So, if you've ever gone to the hardware store to buy an epoxy glue or an epoxy resin, it comes in two tubes, right? You've got, and one of them is like called a curing agent or something like that, but you're literally supposed to not mix the two until you're ready to go. Sometimes it comes in a dual syringe and you just push both of them down and then you stir up really quick and then you gotta slap that on whatever you want to glue and then move on. Have you done that before? Seen people do it before? Apparently surfers do this a lot. You can do that on a surfboard. For what purpose? Not sure. Is it to put on the little fins or what is it? To fix it if it's busted? Okay. No idea. I am, given my experience at Sundance where my shoulder still hurts because of that stupid thing I did, I am too old to learn how to surf. So anyway, here is one of the components of epoxy glue and resin, okay? It is prepared from a molecule called bisphenol A. You will have heard of this because this is a common component of a lot of polymers, and it's actually an estrogen receptor agonist with some affinity, and so there's some concern about products, especially those involved in human consumption that contain bisphenol A or BPA. If you see products labeled BPA free, it means they're not using this. In any case, you take bisphenol A, you deprotonate the alcohol to make it a good nucleophile, and then you use this interesting reagent. We're not going to worry about why the oxygen attacks the chloro instead of the epoxide, but this chloroepihydrin, I think it's called, this generates a bis epoxide reagent. It's got two reactive handles, an epoxide over here and an epoxide there. And that's in one of the tubes. Then in the other tube, you've got a nucleophile that can react with the epoxide. This is a curing agent, and it's usually a diamine where R can be any number of things and proprietary and whatever, but it connects the two amines to each other. You got a nucleophile with two ends, you got an electrophile with two ends. So now you're seeing the possibility of polymerization, right? One of the amino groups attacks the epoxide, you get a proton transfer step, and then you have, this is the rest of the epoxide. This is that 1-2 substitution pattern we talked about. Do you see how that's the product of epoxide opening? But it turns out that you still have reactive portions of the molecule. Amines are great because they can be nucleophiles multiple times. This now secondary amine is actually more reactive than its primary amine starting material. So this can attack another epoxide to give you another 1-2 pattern. Okay? So now I've brought two bis epoxides together attached to the same amine, and remember, each of those bis epoxides has another reactive end. And then we can do the same thing with the other amine, another epoxide opening step, another epoxide opening step, to generate, now we've got a molecule, one amine, one bis amine, or diamine, now 4 bis epoxides attached to that, 4 additional reactive handles. And this can go on and on and on and on and on forever to give you a really complicated network like this. There was a lot of copying and pasting involved, so actually not that long. See that you have, let's see, bis epoxide, what used to be bis epoxides connected by diamines. And it can be more, the structure doesn't have to be this regular. I've just made it look that way to show you that there's a huge cross-linked network. How does this work as a glue? Well, the liquids the liquid mixture of the epoxide and the curing agent infiltrates porous surfaces on the two things you want to glue together, and then it cross-links and hardens, and it's almost like now the two things are part of the same solid. My colleague Paul Savage, if you come up here sometime after class, likes to demonstrate the effectiveness of epoxide glue by gluing a quarter to this table, which really ticks off the custodial staff, and then you can measure the strength of the glue by how long it takes for the quarter to disappear. And there are occasionally, maybe not here, maybe they've sanded them away, but there are occasionally, if you don't see it here, check it in W2023, spots where you can clearly see that somebody has pried off a quarter, and that's Paul Savage. Maybe we'll do that next time, I don't know. Yeah? Okay. We'll see you Friday. I don't know. You would think it would be hard, I don't know this, but you would think it would be hard, for example, to glue two metals together. But I know there's something that does, like JB Weld can totally do that. So, I don't know. It's a good question. Yeah, you bet.
Is it going to be important to know that your basic conditions are nucleophile is going to attack the less substituted?
Yes. We haven't talked about that. That's when I said regioselectivity of epoxide opening. That's what I meant.
Okay.
It depends on whether your nucleophile is basically strong enough to attack directly, or whether you protonate the epoxide first.
Okay.
Yeah.
Thank you.
Yep.
How much longer is the exam review available for?
It's still on. I think I'll leave it up at least until early next week.
Okay. I'm
So,
just trying to make sure
yep.
it's good
Take your
to find
time. Yep.